Hello, chemistry students. We're here to introduce the last unit of the year for honors chemistry, where we take a look at chemical equilibrium.
Yep.
So for our first slide, we're going to introduce the concept of equilibrium and go over the goals. We want to, first of all, describe a system at equilibrium.
And then we want to explain dynamic equilibrium.
Because chemical equilibria are dynamic in nature. And then lastly, to explain the conditions necessary to have a system that is in dynamic equilibrium. And this is a really important concept in a lot of chemistry when we have reversible reactions. So let's get into it in a little more detail.
So to define dynamic equilibrium, it is a state where changes are still occurring at a molecular level, but the macroscopic properties of the system, concentrations, appearance, masses of components, are
pH, all that kind of stuff we can measure,
remain constant. So the requirements for this dynamic equilibrium is you have to have a closed system and a reversible process and or reaction.
And I said put process in there because there's also equilibrium when we're talking about dissolving. Like when you have a saturated solution, say, if we have a solution and we've got crystals on the bottom sitting there, and there's dissolving happening, but then there's also crystallizing happening at the same rate. We also see that with like solubility of gases, and we're going to look at that later on. And it can be a chemical process. If we have a chemical process where A and B are forming some product C, if it's a reversible process, we can have dynamic equilibrium when that goes on.
All right. Alright, so what we have here is a silent video to give you I would say a large scale version of an equilibrium reaction. We have A, which is going to be a beaker, shown on the left side, and it currently has about 500 milliliters. And then on the other side, the beaker 2 has 0, and we're going to illustrate that as A goes forward, it initially will put stuff into the other beaker, and then back and forth. So just watch. There we go.
I think we're always going to put one of the bigger beaker full from left to right, like that, and then two of the smaller beaker going back from right to left. Now you're going to notice we're not filling that smaller beaker initially, are we?
Nope.
So the backwards reaction isn't happening as fast
So
as
after
the forward.
round 2, the next start point is going to be about, what is that, 400?
About 450, I think. And that was like 50. And we'll pause it right here.
Well, I guess we won't pause it. But you can see
Then we went to about 400.
went to about 400.
400.
And the other one
Around
about 100. Yep.
And now
And you can see that the beakers are now both being completely filled each time. We're going to end our equilibrium at about 400, 100 doing this process.
actually at the end of it ends up about roughly 400, 100. It's not exactly, it's a little more like 425.
Yeah.
But we're at equilibrium now. At the end of every round, it's kind of stable, even though water's being transferred. And I think that's the point that we want to make is when you're at equilibrium, it's not that a reaction or a process stops.
Yep. It just keeps going.
It's just that it's going forward at the same speed as it's going backwards. And so our amounts of material, the amount of water in this beaker staying roughly right about there, the amount of water in this beaker staying roughly right about there, and as long as we don't change the process in any way,
Yep.
we're going to stay there right at equilibrium.
Now the thing you have to realize is we can't do this, but in a real chemical system, that one beaker and those two beakers are actually being transferred simultaneously.
Right. I didn't have enough arms to make that happen when I was recording the video, but so yeah, the forward process and the backward process are just happening at the same rate. Okay, so Mr. Hunter's not going to be able to be with us for the rest of the video, but let's go on. So we looked at kind of a model with transferring water back and forth. Now let's actually define what we mean by an equilibrium state. So we were at an equilibrium state near the end of that water transfer demonstration when, even though water was being transferred back and forth, the level in each beaker stayed the same. So when we're in the equilibrium state, the forward process rate or reaction rate and the reverse process rate are equal. So we have both the forward and the backward occurring, but our macroscopic properties of the system are stable. So the amounts in the system or the pressures in the system or the states of matter, the amount of matter in each state are going to be stable at that point. So here is how we would represent this for a chemical equation. So we have hydrogen gas and iodine gas, and they can combine to form hydrogen iodide. So we show this double arrow to show that it's a reversible process. And here's what this would look like in a graph over time. So I would definitely recommend you maybe copy this graphic down. So initially, when the time is 0, you have none of the reverse reactions not really occurring. The forward reaction begins at a fast rate. So we have rate graphed up this side. So the rate is very high. Here it's 0 at 0 time. So the forward reaction begins to occur right away. Lots of hydrogen and iodine reacting to form hydrogen iodide. And of course, as they react, there's fewer hydrogens and iodines, so the rate begins to slow. We see this curve begin to flatten. Meanwhile, as hydrogen iodide begins to accumulate, the backwards reaction with the decomposition of hydrogen iodide begins to occur at a faster and faster rate, And eventually you get to the equilibrium state, which is of course where our reaction rate for both of those processes is the same. So that's what an equilibrium reaction would look like if we graph time against reaction rate. So let's kind of cover what are the requirements, or review what are the requirements for a system to be in equilibrium. So first of all, it must be a closed system where you're not adding or taking any energy or matter in or out. So you're going to have a constant temperature, the pressure is constant, no matter entering or leaving. And it has to be a process that is reversible. So examples of common reversible process would be a lot of different chemical reactions. Not all of them. There are some kind of, like combustion is not a reversible process normally, but many chemical reactions, including a lot of like the dissociation reactions, the neutralization reactions we've seen in acids and bases, they can be reversible. Dissolving versus its opposite process, crystallizing, are reversible. State changes, we can melt water, we can freeze it. Many of these in a closed system are going to be systems that reach equilibrium. Okay, so here we have, let's kind of look at a closed versus an open system. So on the left we have a closed system. Okay, on the right we have an open system. So this would be a soda can, let's say, and the red dots are going to represent carbon dioxide that's dissolved throughout the soda. Now when the system is closed, it's going to reach equilibrium as long as we hold the temperature constant. So basically the amount of gas molecules up here in the space above the soda that we call the headspace is going to be a constant. The amount of gas molecules down here dissolved in the liquid is going to be a constant, and this would be carbon dioxide gas. But what we're going to have is, at any given time, some of these carbon dioxide molecules are going from the gaseous state into solution, so they're dissolving, and an equal number are escaping back into the solution. So our total amount up here and total amounts down here remain the same. Okay, so we would expect our pressure to stay constant. Okay, our CO2 amount to stay constant, and our pH, which is in the soda, is affected by dissolved carbon dioxide, which actually forms a weak acid. It's a Bronsted-Lowry acid when it dissolves, and it actually generates some hydronium ions. So the pH is going to remain constant. Now if we open the lid of the soda, like we see on the right, okay, now we're not going to be at equilibrium anymore, because what's going to happen is once a gas molecule escapes from the solution, there's nothing to stop it from going right out into the air. And yeah, I suppose the carbon dioxide could come back, but we're going to have a lot more leaving and going out this way than we are coming back this way at normal atmospheric pressure, because there's not a whole lot of carbon dioxide in the atmosphere. Okay, so what we're going to see is the pressure in this case is going to be constant, but it's going to be much lower than the pressure in this system over here. And the carbon dioxide is going to end up decreasing in the solution, so we're going to end up with fewer and fewer carbon dioxide molecules in here over time. The soda goes flat. You've all experienced this. Okay, the pH, what we're going to find is that it's going to increase over time because less and less carbon dioxide is dissolved. So a lot of people think flat soda tastes different than carbonated soda, and in fact a lot of that taste difference is due to the change in the pH when the soda goes flat, because the pH rises and it doesn't taste quite as sharp and bitey as it does when it's carbonated. So anyway, just a review of the requirements for a system at equilibrium. So we'll leave you in our introduction to equilibrium with two post-video questions. Question 1. Which condition is not a requirement for dynamic equilibrium? So you have 4 choices. Write down the letter and the description of the choice that you pick. Second question. I want you to refer to the table below. And it's showing how the concentration of acetic acid is changing over time as it ionizes. So you can see that the initial concentration is higher, and as we go down, the concentration is dropping because the acetic acid is ionizing into acetate and hydrogen ions. The question is, at what time was the equilibrium reached, and how can you tell? So you're going to need to give this chart, this table, a little study to answer that question. Have at it, and we'll discuss it next time in class.